So today's lecture is on Anova, and it stands for Analysis of Variance. Okay, and Anova is used to compare more than two population means. If we have exactly two population means comparing two populations, we've discussed that in previous material, and we have used the t-statistic to compare two population means. Okay. So this is a new methodology, and it applies when we have more than two population means. So here, I want you to consider this case study of iron deficiency. And iron deficiency is really important. It's one of the most prevalent micronutrient deficiencies worldwide, and an estimated 2 billion people are affected. This deficiency may be caused by a variety of factors, including insufficient iron intake, which is really a key word for not eating enough foods that have iron-rich content. The consequences of this could be complications of anemia, and this depletion of iron stores and reduces the iron availability to the arteriocytes and other tissues, and it reduces the hemoglobin levels. So HB stands for hemoglobins. That is indicative of anemia. Okay. Short-term effects can include depression, depressed immune and endocrine function, increased likelihood of infection or illness. So iron intake and hemoglobin levels are synonymous, and they're really important for this iron deficiency. Okay. So we have data that was collected from 140 volunteers as a cross-sectional samples across 5 areas. One-day clinics were set up, and individuals were asked to participate. Blood samples were taken, which allowed us to measure hemoglobin and hematocrit levels as biomarkers. Okay? So here's the research question. The first, most basic one is that hemoglobin levels in each geographic location. We want to know if they are the same, the average hemoglobin level. Okay? So at these 5 locations, is the mean hemoglobin level the same? Okay, and so the null hypothesis is always that all the means are the same in ANOVA versus the alternative, which is that at least one population mean is different. Okay, and I'm going to tell you that we're going to use this ANOVA F test to compare 3 or more population means. Now, researchers believe that Larabanga has a hemoglobin level that is higher than the others. So this was because Larabanga was located close to a national park, and they had more access to meat and iron-rich foods than other locations. Okay, and so they want to know if that was the case, if that access had affected the hemoglobin levels. Okay, and so I just want to discuss one thing that's just a review for basic probability, and that's if we perform 5 tests and each test correctly identifies the true result 95% of the time, and each test is independent, then the probability at least one test out of 5 is incorrect is given by this complement and multiplication rule. And that's a 22.6% chance that you make at least one incorrect conclusion or comparison. Okay, and ANOVA helps to address this issue. Okay, so instead of using t-tests, we'll use an ANOVA test, which is one test against all the population means, instead of testing every single possible comparison. So just to clarify, in Anova, the null hypothesis is that all the means are equal, okay? And the alternative is that at least one of them is not equal, okay? Now, Anova has certain assumptions or requirements to perform. One of the assumptions is that each of the populations has a data set that's obtained from a random sample, either a simple random sample or a randomized experiment with K treatments. Each of these K samples are independent of one another, i.e. each population is independent of the other, and each of the populations should be normally distributed, and each population has the same variance. Now here's a brief remark. It says that Anova is robust, meaning minorly violating these assumptions is okay. We would expect it to work. Okay. It's important to know which assumptions are violated. The equal variance is the most important, and your book suggests that the largest population standard deviation is no more than twice the smallest. So that is the largest extent that they expressed that should be the violation. Now, this is a hard and fast rule. It's just a recommendation. Okay, so we're going to use this box plot of the hemoglobin levels by location to assess these assumptions. Here, these box plots are not perfectly symmetric, but relatively, right? The lower fence here is greater than the upper fence. Here, the median is closer to the third quartile than exactly in the middle. And here, this lower fence is extremely low. So this one seems like it's probably not perfectly normal, but by and large, most of the box plots seem reasonably normally distributed. Okay, so we are expecting some violations to normality based on the box plot, but it doesn't seem excessive. Okay, now the other thing is that the variance, which is the ranges for which these quantities fall, are they equal? Well, we can see that the range from the upper to the lower here is not the same as here. So Jamestown to King Tower, and likewise University of Ghana is much different than all the others. It looks like this assumption of equal variance is not perfect and that there are violations to equal variance. Okay. So if we go ahead and assess this, independence seems to assume that one individual, regardless of what population they are in, should not affect the other's hemoglobin level. The data as described in the study is not a random sample. But it may be used to the extent that the data represents the population. Okay, and I don't have any big reasons to believe that it doesn't represent the population, but it's not truly a random sample. Okay, the box plots indicate normality as reasonable, but that they're slightly skewed. Okay, it has a general indication that the variability in the data suggests that the variance in spread is approximately equal, but not perfectly. Several locations have variances that are larger and smaller. And we believe that these violations in Anova are minor, and the test is robust, so we're relatively safe to proceed with the analysis. So now that we've discussed the null and the alternative hypothesis and assumptions, what is the Anova F test and how do we do it? Okay. Well, the Anova S test is computed in this way. It's the mean square error due to treatment or population divided by the mean square due to random error. And we're going to abbreviate this by MST divided by MSE. That's the F statistic. Okay. This provides a numerical measure in favor of the null hypothesis or the alternative. And the idea is that if each mean in the K groups or treatments are the same, the mean square due to treatment does not change, and the means and the difference in the sample mean are due to random error. Okay? So if there is a difference according to treatment or population, I'm expecting that mean square treatment will be large relative to mean square error. And mean square error is the total amount of error across all populations. So that this one will stand out. Okay. If the mean square due to treatment, if there isn't an effective treatment or population, then I'm expecting that this quantity will be relatively small. Mean square due to treatment should be relatively the same as compared to mean square error. So a small value of f indicates that the null hypothesis is true, and a large value indicates the alternative is true. Okay. So if we're doing the Anova F test, here are some of the terms that are used. Okay. And this is what I said verbally, just the logic. Okay. If at least one of the means in the treatment are different, then the mean squared due to treatment group should be larger than the random deviation in the error. Hence, the mean squared due to treatment is large relative to the mean squared due to random error. Okay, so terms that we're going to encounter: K is the number of groups or treatments. S sub I squared is the sample standard deviation from group I. So, and I should say this is not the sample standard deviation, but the sample variance from group I. And n sub I is its sample size. Okay. X bar is the sample average of every single data point regardless of group. And xi bar, that's the sample for only the data points belonging to treatment I. Okay, so our Anova F test, it has a sum of squares due to error, or SSE. And this SSE is calculated by n-1 times the sample variance plus n-2 times the sample variance. And I add them all up. I repeat this process. So that's the mean squared due to error. Or excuse me, that's the sum of the squares due to error. And the mean square error, that's just the average. So you take SSE, that's the quantity above right here, and you divide by n minus k. Okay, n is the sample size and k is the number of groups. Next, we have the sum of squares due to treatment. This is n1 times x1 bar minus the overall average square. So if one of these quantities, the average treatment due to treatment 1, is much different than the overall treatment, we'll expect this quantity to be big. So SST is going to be add up all these quantities, and the mean square due to treatment is just take the average of the k treatments. So take that quantity that was above and divide by k minus 1. K is the number of groups or treatments. So I can summarize this as SST divided by k minus 1, and your F test is just take the ratio of MST, that's here, divided by MSE here. Okay, and you'll commonly see what's called an Anova table. An Anova table consists of the following information. It has the source of the variation, that's the treatment, the error, and the total, that's the addition of these two. The sum of the squares is the sum of the squares due to treatment, the sum of the squares due to error. Those are the things that we talked about here and here. We have the degrees of freedom, so that's number of groups or treatments minus 1, our sample size minus the number of groups. When we add these together, we have our sample size minus 1. So sometimes I like to ask you, if I give you the degrees of freedom according to this table, I will sometimes ask you how many observations were in the study. Okay. And then you can form your mean squares, your MST. That's just the ratio of this divided by this. This divided by this. And then you form your F statistic. Now, I'd like to point out, if I provide you with this information, not even that information, just this information, you can fill out the rest of the table. Or if I was to provide you with just these 2 bits of information, you could fill out the rest of the table. So this is kind of like a puzzle. I don't have to give you all of the information in the table. I can give you parts of the information and ask you to calculate these other terms. Like I give you this and this, ask you to calculate F statistic, ask you to calculate sum of squares. I can give you this and this, ask you to fill out everything else. Okay? I can play with the piece of information that I give you. Okay? So going back to the Ghana study, here's the source of variation. It's the location, the residuals. Here's the degrees of freedom. Notice there were 5 locations, so the degrees of freedom is 1 less, it's 4. The residuals is 133. Okay? And I have all of this information. So if I want to get mean square, I'll just take this 40.5 and divide it by 4. Okay. If I want to get this number, I'll take this number and divide it by that. So I get the F value by taking this value divided by this value. And this is my p-value. It's 0.0677. So now, based on this table, by the way, this p-value was provided in the output, but you can use the calculator, and I'll show you how to do that, to calculate it in your book. If you're using an Anova table and your p-value is 0.06, you might fail to reject the null hypothesis of equal means at the 5% level of significance in favor of the alternative. So you would conclude that each of the 5 locations has the same mean hemoglobin level. Okay. So let's go ahead and calculate this p-value, 0.06. So our F value is 2.24. I have 4 and 133 degrees of freedom. Okay. So let's go to our F distribution calculator. Our F value was 2.24. The numerator degrees of freedom, well, that is this, because we take this divided by this. So that's 4 for the numerator, 133 for the denominator. So 4 degrees of freedom for the numerator, 133 for the denominator, and get 0.0681. That's pretty close to what we got here. I had a different calculator that did this. So it seems reasonable to get this value. Okay, here's another data set. It says the results from an experiment to compare yields as measured by dry weight of plants obtained during a control in 2 different treatment conditions. Experimental units are randomly assigned to a control treatment group 1 or treatment group 2. After the treatment is complete, we compare the yields of each treatment. So the question is the yield of the 3 groups equal, or does at least one group have a higher yield? And we're asked to test this at the 5% level of significance. So we're going to do Anova. This is our test of hypotheses that the control, the treatment, the first treatment and the second treatment all have the same output, versus at least one population mean is different. Okay? So let's begin by investigating this, and let's investigate with a box plot. So here's our control, here's the average weight, the median weight in a box plot, and here's from treatment 1, and here's from treatment 2. Looking at this box plot, it looks like the data is not perfectly normal, but that there are minor violations. It looks slightly skewed, like look at the placement of the median in control versus treatment. Here it's perfectly in the middle, so this one looks nice and normal. Okay. The equal variance, it seems reasonable, but if we look at treatment 1 compared to treatment 2, there's a lot more variation here than there is here, so it seems like it might be weakly violated. And here's what I have to say about that. So from the box plot, one of the things that stands out is that treatment 2 has a higher yield. Look at this box plot. It's all the way up here, way above treatment 1. The control, it's harder to assess by how much it's above it, but it looks like there's definitely a difference between treatment 1 and treatment 2. Okay. The samples are independent. They're the yields of the corn, the yields of the plants, and one, it seems reasonable, one should not affect the other, at least in the treatments. And the box plots suggest the data could be normally distributed. It looks slightly skewed. One thing that I didn't mention is that the sample sizes here are relatively small, so it makes it hard to assess the normality and the variance. Okay, the variance doesn't appear to be equal, but it's hard to determine based on the sample size. And we believe that this violation is with an acceptable margin of Anova. Now, one good thing about this data is that it's obtained from a designed experiment. So we can infer causation without any confounding variables. Yep. So here's the Anova table. Here's the source of variation due to the group. Notice there were 3 treatments, so the degrees of freedom is 2. The residuals is 27. And here's the rest of the table. Sum of squares, mean square, f-value, probability. Okay. Based on this p-value, there's strong evidence that the treatments do not all have the same mean. Okay. And this p-value is calculating, you can use that f distribution calculator as we did before and calculate this value. Okay. One question I asked here is how many observations are in this study? Okay. Based on the Anova table. If I add this and this, 2 plus 27, that gives me 29. That's the number of observations minus 1. So if I add 1 to 29, I get 30 observations. I ask you, what is the relationship between mean square column and sum of squares column? So here's the mean square column, here's the sum of squares. The answer is that this number is obtained from this number by dividing by its degrees of freedom. So you take this column and divide by the column in the degrees of freedom. Okay? So I answer each of these questions and I address this. Okay, and one thing that I would note is that the F statistic I got this 4.84 by taking 1.88 and dividing it by 0.388. Well, that's nothing more than taking this divided by that. Okay, now since the p-value is less than 0.01, it's significant at the 5% level of significance, and we reject the null hypothesis in favor of the alternative and conclude at least one treatment has a larger yield. Now, in order to determine which treatment has a larger yield, we need to perform a post hoc test to determine which ones are different. Okay, so let me tell you what is a post hoc test and how do you interpret the output. Okay, now a post hoc test should only be performed once you reject the null hypothesis of an Anova. Okay? And it tells you which 2 population means have different yields. So to compare each of the K treatment populations, we use what's called a 2-key HSD test, and HSD stands for honest significant differences. It helps mitigate the chances of making at least one error when performing repetitive t-tests. Okay, and now let's look at the post hoc test, and this is the plant growth data set, by the way. The post hoc test gives us this. It compares these groups, treatment to control, has a difference of minus 0.37. But what I'm really interested in is this 95% confidence interval. If this 95% confidence interval contains 0, it means that there's likely not a difference. Or I want to pay different attention to the p-values, the adjusted p-value. So if this p-value is like less than 5%, I can reject that these two are different at the 5% level of significance. So looking here, it doesn't look like it's significant at the 5%. This is bigger than 5%. This one's bigger than 5%. And as well, if I look at the confidence interval here, it contains 0. But I can go to this one. It has a p-value of 0.012. That's less than 5%. It indicates that these two groups, treatment 1 to treatment 2, is different. The estimated difference is 0.86 in mean difference. Okay, and this difference, it's significant at the 2% level of significance. We're up to 0.12. Okay. The lower estimate for the difference is 0.17. The upper distance is difference estimate is 1.55. Okay. So this tells us by how much the difference could be and what it's estimated to be. It's estimated to be that. It could be as small as that or as large as that. That's the 95% confidence interval. This does not contain 0, so it indicates that truly these two are different. Okay. So here's our conclusion. Based on the output of the post hoc test, from either the confidence interval or the p-value, we conclude that there is not a significant difference between group 1 and control and group 2 and control. But there is a difference between treatment 1 and treatment 2. And those are evident from the box plot. Okay? So that's awesome. That concludes Anova and post hoc tests. Thank you for joining me, and thank you for a great semester.